In this video, we discuss ARMA process, which is simply a combination of AR and MA processes. We also discuss how to identify the ARMA process with the help of ACF and PACF diagrams. Next, we discuss in a step-by-step manner how to build an ARMA model for forecasting. We also discuss the prediction process with time series models and compare it with the prediction process with structural models. With a simple example, we discuss how to forecast with ARMA models. We also discuss forecasting terminologies with one step ahead and multi-step ahead forecast and rolling versus recursive sample forecasting. We also discussed how to determine the accuracy of out of sample forecasts. In this video, we'll introduce ARMA, which is autoregressive AR, and moving average, which is MA. So in this video, we'll introduce ARMA process, which is a very important component of ARIMA models, ARIMA class of models. Just to make a distinction here, I here is nothing but the integration of the process. So depending upon the levels of non-stationarity, and we'll define it in subsequent videos, depending upon the level of non-stationarities, the order will be integrated of that order. And other than that, the most important part of that ARIMA is AR and MA, which we are going to discuss in this video. To put it succinctly, an MA process is nothing but a combination of AR and MA process of different orders, say P and Q. So if AR process is of order P and MA process is of order Q, and we combine them, we get an ARMA process of order P and Q. Mathematically, the notation is YT as a combination of its own past values, these YT minus 1s as we did for AR process, and a combination of white noise processes, which is mu T minus 1 and so on. So this is our ARMA process. Now, as we have already seen, we can put both these AR and MA terms in a more compact notation like this, where phi L is nothing but 1 minus phi 1L minus phi 2L square and so on, the algebraic polynomial. Similarly, the theta L or the MA process can be written as 1 plus theta L plus theta 2L square and so on, which is the algebraic notation. Also, we said that muties here are white noise processes, and these muties, the white noise process that these muties are, can be defined with the expected value of 0, their variance, which is expected value of mu t square as sigma square, and their autocovariance as 0 for all the times which are not same as S. For all the T's that are not same as S, the autocovariance is 0 because white noise is a process with no discernible structure. What about the ACF and PACF plots? Interestingly, being combination of AR and MA process, the ACF PACF plots are sort of combination of AR and MA process taken separately. For example, if we put them together, both the ACF and PACF plots are exponentially declining in magnitude irrespective of their order. For example, look at this ARMA process of order 1, 1, ARMA 1, 1, because here AR term is order of 1 and MA term is also of order 1. So this is ARMA 1, 1 process, and it has exponentially declining structure, which is sort of combination of AR and MA itself. If you recall, AR had exponentially declining ACF while cutoff of PACF same as the order of AR process. For MA process, it was exponentially declining PACF while ACF was cutting off at exactly the same as number of order of MA process. If we combine them both for AR and MA, if we combine these terms, we get both ACF and PACF, which is exponentially declining for both ACF and PACF, and that's how you can exactly identify and differentiate between AR, MA, and PAC ARMA model on ACF PACF diagrams. To summarize, ARMA processes are nothing but a combination of AR and MA processes and part of a very wider class of ARIMA models. I in ARIMA would show the level of integration or sort of non-stationarity, what is the characteristic of non-stationarity depending upon the order of non-stationarity, whether it is level 1, level 2, the I term would be there. But in finance and economic series, mostly the I part is modeled separately and then the remaining part is modeled as ARMA model. So for example, if a process I2, first we'll try to remove the non-stationarity of level 1 or 2, whatever it is, and once you model out non-stationarity, you'll focus on ARMA part of it in modeling through an expression like this. And lastly, between AR, MA and ARMA process, you can differentiate between them using the ACF and PACF plots visually. For ARMA process, both the ACF and PACF are geometrically declining, which is different from ACF and PACF for AR and MA processes separately. In this video, we'll introduce to building and estimating ARMA, AR, MA class of model. Starting with ARMA model, the first step is identification of the ARMA process. That means understanding what is the order of AR and MA terms, P and Q, order of AR process and order of Q process. Once you understand the structure and order of the model, then second step is estimation of these parameters. For example, if it is a ARMA PQ model, you have parameters, that is coefficients corresponding to AR and MA process, that you will try to estimate with process such as OLS and MLE. OLS is ordinary least square estimation and MLE is maximum likelihood estimate depending upon the context and nature of model. For example, OLS is more suitable to linear modeling, while MLE approach can be used for non-linear as well as linear. Then we come to as last step as model diagnostics, that is you test the model. Generally you try to test the residual of the model. That residual should be, generally the assumption with residuals is that they are white noise terms, so they should have no autocorrelation structure. That is one. Often the model is also tested for overfitting. For example, you start with an overfitted model and then you test the parameters whether they are significant or not. So you keep on eliminating insignificant parameter to arrive at a very parsimonious model. The idea behind using a parsimonious model is to choose as less number of AR and MA terms as possible. A parsimonious model has two very good properties. First and foremost, it consumes less degrees of freedom, which means observations or data observed, resulting in lower standard errors. So if you have a parsimonious model relative to a bulky and more complex model, it will consume less degrees of freedom and result in lower standard of errors. That means good and high power of test. The second part is overfitting. So a model which is bulky and complex and not so much parsimonious may have a problem of overfitting. That means it may fit to data specific properties, which we often refer to as noise also in physics parlance. While a more parsimonious model has less tendency of overfitting and it may rather fit to important properties of data, which is often referred to as signal in physics parlance, and which means the implication is that a very bulky model may give very high and good fit with a given sample on which it was trained, while in out of sample, a new data, it may perform poorly. In contrast, a parsimonious model may be relatively not as efficient in a given set of data in which it was modeled, but its relative performance on out of sample data would be extremely good. How do we choose between two competing models? So there we use something called information criteria for selecting different lags or structure of ARMA process, that is PQ order, ARMA orders, that is PQ terms. We have three famous AIC Akaike information criteria, Schwartz information criteria, and also Hanquin criteria. These criteria are nothing but a combination of two terms. The formula is different, but essentially they are combination of two terms, sort of trade-off or two competing parts. First part, this part which is log L, which is the log likelihood function, sort of log likelihood function, which is computed based on the residual errors from the model. As you keep on increasing the parameters, there are two competing effects at play. These residual errors will come down. So as you keep on adding more and more parameters, this first term will go down as residual errors will go down. However, the second term, which is K, increases with parameters, so number of parameters. So the two competing effects, residual, this term represents residual. For example, here this term represents the decline in residuals with the addition of new variables, while the second term, this term, captures increase in number of parameters. So you try to choose AIC value which is lower. K here is K by T, where K is number of parameters, small k is number of parameters, and T is the sample size. Log L, like I said, is the log likelihood of observing the parameters. Essentially, it is computed from the residual squares. So here these two competing effects are at play, and their net, which is the AIC information criteria, they are used to compare the models with different structure, or that is different order of the process, ARMA PQ process. So to summarize, in this video we discussed how to build, estimate and test an ARMA class of model, and while deciding the structure of model, how do we select the lags of AR and MA terms using the information criteria AIC, BIC and HQIC criteria. In this video, we'll introduce forecasting with time series models. We'll also discuss and compare them with structural models of forecasting and prediction. To begin with understanding the time series forecasting process, let us understand this notation, that is conditional expectation of yt plus 1 given information up till time t. So this notation, expected value of yt plus 1, given information, this omega t is for information up till time t, it is called conditional expectation of this value y at a time t plus 1 given information available omega t up till time t. This is this notation. Similarly, we can write it for time t plus 2, t plus 3 and so on. Now let us think of a zero mean process like white noise process mu t. Its conditional expectation at time t plus 1 given time t is said to be 0 for all s greater than 0. So for all future periods, its forecast, the expected value of its forecast is 0. There are two very simple methods of forecasting. One is called naive no change forecasting. This naive forecasting method suggests that forecast of a series y at time t plus 1 given at information time t is nothing but its previous value yt at time t. This is also more applicable in the random walk process where the process is purely random and therefore the best forecast of tomorrow is whatever the value today. So therefore the conditional expectation of the series y at time t plus 1 given that all the information and values known at time t is nothing but the value at time t itself, which is yt. This is also called no change forecast because we assume that future value, the best estimate of future value is today's value itself. There is another set of processes which are mean reverting, which are expected to revert to their long-term mean, and therefore in that case the unconditional expectation is taken, and that unconditional expectation of mean of y is taken as forecast, sort of long-term mean. So in this case, for a process which is mean reverting, which is known to revert towards some kind of long-term mean, the unconditional long-term mean, what is unconditional? That we have taken the mean over a long horizon, not specific to a particular information, but over a long horizon, that unconditional mean is taken. It is also, in other words, this is some kind of long-term average that is used to forecast at any time t. Now this long-term forecast remain valid for whether you are looking at t plus 1 or t plus 2 or so on, and therefore this is unconditional. This is unconditional at what time you are looking. Is simply the unconditional forecast. So we simply write expected value of y t plus 1 is equal to that long-term mean, or expected value of yt plus 2 is equal to that long-term mean. Now notice there is no conditional. This conditional omega t term is not there, which means that this is unconditional. Now let us compare these time series models and forecasting with time series models with structural models. A structural model would look something like this: yt equal to beta 1 plus certain explanatory variables like x2t, x33 and so on, xkt, and their coefficients, and then there is this error term, this you can think of as a white noise error. When you are forecasting or predicting with this kind of structural model, which is obviously driven by some kind of theoretical underpinning, the conditional expectation of yt at time t with given information at t minus 1 would appear something like this. However, this kind of forecasting, and because these betas are constant, they are sort of population parameters, so they are taken out. So inside expectations operator, we have taken expectations on both sides. We have x2t, x3t. These are the values in the expectation. Now, in order to conduct the forecasting or prediction, or what we call as conditional expectation of yt, we need forecasts of x2t, x3t, xkt, which are time series processes themselves. And that makes this prediction with the help of structural model extremely complex process, because now you have to rely on all those k variables and do the modeling and prediction for these variables themselves. This is a difficult part, and therefore one may have to examine the historical values of all these x's, maybe find their some kind of mean or expected values. First you have to find their expected values, and then in turn you have to forecast the expected value of yt. However, rather than going through this cumbersome exercise, if you are relying on simple time series model of yt by modeling through its own values like yt minus 1, yt minus 2, and the white noise information shocks mu t's that have arrived currently and previously, you can very easily model yt without considering these values. The idea here is that this structural relationship or any other kind of structural relationship will remain anyway valid, and therefore this relationship will remain also valid historically. That means for yt minus 1 and yt minus 2, and therefore when we are modeling yt with yt minus 1, yt minus 2 and so on, essentially we are factoring these relationships that have appeared or captured their information historically. So this relationship, the information pertaining to such structural relationship, is in historical terms is already captured in yt minus 1, yt minus 2, and therefore when I'm modeling yt with its own historical values and white noise error terms such as this through some kind of ARMA process, I'm essentially, without even going into this structural model, I'm factoring this. And therefore, this kind of modeling is extremely powerful, that it saves a lot of time and effort in modeling the structural model and able to capture the information content of this structural process itself. So to summarize this video, we have understood what is time series forecasting, what are the elements of time series forecasting, and how it is a better way when we are doing some kind of future forecast or prediction as compared to structural models. While it takes the information content of those structural models, still it saves or avoids a lot of problems in terms of information collection and information gathering and building cumbersome models as done with the structural models. In a series of next few videos, we'll try to understand forecasting process with ARMA class of models. In this particular video, we'll understand forecasting with MA model. Let us examine this simple ARMA PQ model at time t with s steps into future. The forecast would appear something like this. Notation is ft plus s, representing at time t s steps at forecast. Now it will have two components. First, AR component, that is its own previous terms. If the actual value is not available, then forecast f will be employed, which is the previous values of the series itself, and its coefficient AIs, which are autoregressive coefficients. And then you have MA terms, white noise process mu t, his previous values and current values of mu t with MA coefficients. So let's start with forecasting of MA process. Let us take a simple example of MA 3-order process, yt equal to mu. This is the constant term which we assume some kind of long-term constant value which is known to us from historical experience. And then three terms, mu t minus 1, mu t minus 2, mu t minus 3, and their coefficients theta 1, theta 2, theta 3, and the current information or innovation shock mu t. We'll assume parameter constancy that this theta 1, theta 2, and theta t will remain unchanged as we move ahead into future. So if this relationship holds, the one step ahead forecast yt plus 1 will be obtained by simply just adding 1 in this subscript. So the model will become mu plus theta 1 mu t plus theta 2 mu t minus 1, and so on up till theta 3 mu t minus 2 plus mu t plus 1. In this model, we can obtain the forecast by simply taking expectation, which is the forecast is essentially nothing but conditional expectation of yt plus 1 using information available up till t, that is conditional up till sigma t. So we'll apply the expectation operator, and the constant terms such as mu and theta 1, theta 2, theta 3 will remain unchanged and will be taken out. However, one important point, till now we have been saying that the conditional expectation of error term as 0 because these are white noise processes. However, when we are standing ahead in today, all the information or these information shocks, what we are, if you recall, we said these white noise processes are nothing but being white noise processes are used to model the information shock that has arrived in the process. So whatever information shocks have arrived till date, they are already known. So their conditional expectation is not 0, we'll not take it as 0, but we'll use the actual values. So for example, up till information t, up till time t, we have all the information available. So for that, we'll use the actual observed values of mu t minus 1, mu t minus 2. However, for mu t plus 1, because this is not known, its expectation obviously will be 0. So expectation of this mu t plus 1 will be 0, but the conditional expectation of these terms mu t minus 1, mu t minus 2 will not be considered. Their actual values will be taken. So in this spirit, when we take expectations, this mu t plus 1 will become 0, but for all the other terms, we'll use the mu plus theta 1 mu t plus theta 2 mu t minus 1 plus theta 3 mu t minus 2, with the caveat that these mu t minus 1, mu t minus 2 are actual values that are already observed standing at time t. So with this being the case, we already have the forecast of ft1 one step ahead in future, which is this. Now let us do the forecasting for 2 step ahead in future, which is ft comma 2, which is nothing but conditional expectation of yt plus 2, again using the information up till time t. Now in this case, we need to add the subscript here plus 1. So for each, we will add 1 to subscript, and then we recall that when the expectation operator is applied, t plus 1 will be 0, but for mu t and mu t minus 1, actual values will be employed, and therefore this term will get eliminated, and we are only left with mu, which is the constant term plus theta 2 mu t plus theta 3 mu t minus 1, which is our forecast for 2 step ahead. In a very similar fashion, for 3 step ahead forecast, we'll take the conditional expectation of yt plus 3 given information omega t. So we'll add another plus 1 in the subscript here, mu t plus 2, mu t plus 1. This will become mu t itself. Now, when we take this expectation, again, please note this mu t plus 2 is in future. So its conditional expectation is, that is expectation of mu t plus 2 using information up till sigma t, omega t, it is 0. So this will be 0, this will be 0 because they are in future. Only for mu t, the actual value will be employed. And therefore, we are left with mu plus theta 3 mu t. So this is our forecast for 3. Now, please recall, this is a MA3 order process, order of 3. So only information that is available up till 3 step ahead will be used. After that, there are no mu t's that are actually available. So now all the terms will be in future, that is mu t plus 1, mu t plus 2, and so on. Case in point, 4 step ahead forecast, which is nothing but conditional forecast of yt plus 4 given omega t. Now in this case, as soon as we add 1 step ahead, we have t plus 3, t plus 2 and t plus 1. All these white noise mu t are in future. So their conditional expectations given omega t, which is the information available till t, will be 0. So all these terms will be 0 and we are only left with mu. And I hope you can see where we are going with this. All future forecast t comma 5, t comma 6 and so on will become mu only, which is the constant or some kind of long-term mean of this process. As we said earlier, for practical implications, we'll have this mu as 0. So in that case, if this mu is taken as 0, all these values will become 0. And only those values up till 3 forecast. And why only 3? Because this is an MA3 order process. Since the MA3 order process has a memory of only 3 periods, any forecast of 4 or more periods will converge to that long-term unconditional mean mu or the intercept term. If this is being taken as 0, then this part will become 0 only, and only up till 3 period forecast will survive. To summarize, in this video, we have discussed how to forecast with MA process. We noted that MA forecast become or converge to some kind of long-term conditional mean for any term higher than the order of process. So if it is an MAQ process, any forecast which is more than Q steps, maybe Q plus 1 or Q plus 2, will converge to the long-term unconditional mean, which is the intercept term. If it is 0, then that forecast will be 0. And only those forecasts that are up till Q steps ahead in future will survive for an MAQ order process. In this video, we'll try to understand forecasting for AR processes. Let us consider a simple AR2 process. Its structure would be yt equal to mu, which is again the constant term, may be taken as 0 also, phi1 into yt minus 1 and phi2 into yt minus 2, which are the previous values along with the coefficients, autoregressive coefficients phi1, phi2 and the white noise error term. Now, as we'll see very shortly, that unlike MA process, which was restricted to the number of lags of white noise terms, AR process has an infinite memory. We'll see that. So let's understand what will be the t plus 1 forecast here. So forecast at t plus 1 would be the constant term plus phi1, and we'll add for each of these subscript, we'll add 1. So here we have mu t, yt minus 1, and then this mu t plus 1, which is the white noise error. In this case, when we are computing the forecast for 1 step ahead and by taking the conditional expectation of yt plus 1 at information available up till time t, please recall that up till time t we have yt and yt minus 1 already observed. So we'll not be taking their expectation but actual values because they can be observed. And when we are computing the expected value of this mu t plus 1, because this is not observed, it will become 0. So our expectation operator will operate on this mu, yt minus 1 and so on, but their actual values are available, so they will be taken. But when we compute the expected value of this term will become 0. So we are left with mu plus phi1 yt, phi2 yt minus 1. These are actual values that are observed already because we are standing at time t. In this fashion, we have obtained the forecast, 1 step ahead forecast like this. We can similarly proceed for step 2, 2-step forecast by ft comma 2, which is nothing but conditional expectation of yt plus 2 at time t information available pre time t. Again, we'll add 1 to the subscript, so we'll get yt plus 1 here, yt here, and mu t plus 2 here. Now, while applying the expectations operator, please note that mu is constant, so it will remain unaffected. Yt plus 1 now is not observed at time t. So we have to take its expected conditional expectation, which we have already computed as ft comma 1. Yt is already observed, so it will remain as it is. So we'll have mu, which is the same. With phi 1, we'll have the expectation of yt plus 1, which is ft comma 1, which is nothing but conditional expectation of yt plus 1 given information available up till time t, plus phi 2 into yt because yt is actually observed. Now, I hope we can see where we are going with this. If we compute the third step forecast, which is the conditional expectation at time t plus 3 omega t, we add another plus 1 to the subscript, so it becomes yt plus 2, yt plus 1, and mu t plus 3. The expectations operator will give us mu here, but now yt plus 2 will be nothing but ft comma 2, which is computed in the previous step, and ft comma 1, which was computed in this step. And therefore, our resulting forecast which appears like this, we can obtain a more generic expression. Look at this, ft comma 3 plus mu into phi 1 times ft comma 2 plus phi 2 times ft comma 1. So the generic forecast will appear like this, which is nothing but ft comma s steps ahead forecast with a constant term, immediate previous term s minus 1, and next previous term s minus 2. Why these two terms? Precisely because this was an AR2 process. So that's why we are having these two terms. But with these, we can go ahead infinitely in future and we'll always get a forecast which is not same as mu or 0 as was in the case of MA, which means for every n x steps in future, we can obtain some kind of conditional forecast using previous two values which do not become 0, unlike the case was MA. In MA, as soon as we are ahead of the MA order of the process, which was MAQ, the forecasts were converging to mu, which is the conditional mean, or 0 if in case it was 0. But here, every time we observe some kind of forecast depending upon its immediate previous values, and that is why we said this AR process has infinite memory. More importantly, now that we have forecast for this ARP order kind of process and MAQ as we seen earlier, we can combine them and obtain the complete forecast for ARMA PQ process. To summarize this video, we have understood how to forecast for AR process. We noted that unlike MA process, which were restricted to the order of the process, the forecast for MA process, the forecast for AR process have infinite memory, that they can be made infinitely long horizons. But in conclusion, if you want to forecast for ARMA PQ model, you can separately forecast for AR and MA processes and then add them together to get the complete full ARMA PQ order forecast. In this video, we'll be introduced to some basic terminology related to forecasting models. First, we'll start with in-sample versus out-of-sample forecasting. For example, let's say we have data available from January 1990 up till December 1999. One approach to develop a model is to use the complete data from January 90 to December 1999 and test its fitness, or try to see how fitted values will appear. But this is not a very good approach because generally it is expected that when we are training the data, using this data, training the model would generally do well on this data itself. So a more evolved way is to take a certain set of this sample, maybe January 1990 to December 1998, call it training data set, part of the sample on which the model is trained and parameter estimated, and a certain set of sample which is left out or hold out sample from January 99 to December 99. These set of observations are not used as a part of training data set, and these observations are used for testing the model. So we use certain set, and this is up to researcher how many. Generally a good ratio is 70-30 or 80-20. So on 70 to 80% of the observations, the model parameters are trained, and once the model is trained, we try to predict on these set of observations and then test the model accuracy, which is called out of sample forecasting. So this was the in sample estimation, and this is out of sample forecasting or evaluation of the model period. The next is, what is the forecasting requirement? For example, I may want to forecast for 1 step ahead. Somebody may want to forecast 2 step ahead or 3 step ahead. Generally, it is well accepted that if you go further and further, if you go s steps in future where s is pretty large, your forecasting accuracy decreases. So as a researcher, I should have some idea, some experience about my data, that whether 1 step or 2 step or 3 steps in future forecasts are more efficient rather than a very lengthy forecast. Third is rolling versus recursive forecasting. Let's understand it. So let's say I'm planning for a 1, 2 or some kind of S-step at forecast. A rolling window approach would start with a certain initial set, maybe January 1990 to 1998 December, and then forecast maybe 1, 2, 3 steps in future. Now, when as a researcher, maybe I have found that S steps, maybe 3 steps in future, 3 steps at forecast is good enough for me. So when I'm going to the next 3 steps, there are two ways. Either I can keep my initial window fixed and add the next steps, 1 t plus 1, t plus 2, and t plus 3 in my current set of observations, and then make use of original sample eh, S observations plus these three newly added observations to make the next set of forecasts. Another approach would be to rather than keeping the initial, this is called, the previous approach was called recursive window because the initial period was kept fixed, and as we move ahead in future we keep on adding each observation one by one, we keep on adding to our sam original sample, so our sample size increases. The second approach is to have a rolling window approach where as we keep ahead in future, we add one observation, but at the same time we exclude the last observation. So this January 1990 will be excluded when January 99 will be added. When February 99, February will be excluded and February 1999 will be added. And as we keep on moving ahead, our sample estimation period will remain fixed. That is approximately, this length is 180 months, that remains fixed as we keep on moving ahead. So we exclude one period when we add one period. This is called rolling window approach. Both these approaches have a trade-off. For example, with recursive window, the benefit is that your sample estimation period, in sample period, becomes larger, but at the same time, the previous values that are still not taken away from the sample, they may not be in sync with the current market conditions. They may be probably more stale, and therefore some of the very old values may not be up to the date and may not give me the correct picture. While with rolling window, we limit our sample size to, in this case, 180 or a certain number, but at the same time, as we move ahead, we keep on excluding historical values so that our sample on which we are training the model is more in sync with the current market conditions. So, to summarize this video, we learned some terminologies related to forecasting. These included one-step versus multi-step at forecast. We have in-sample versus out-of-sample prediction and rolling versus recursive method of forecasting. In this video, we'll try to understand how to determine the accuracy of forecasting. As we noted earlier, that often it is important to have model trained on in sample on a given sample data, while use the holdout sample or out of sample, the second cut of sample for out of sample prediction, and then find the accuracy of forecasting on this out of sample prediction set. Let us see and proceed how to do that. Let's say you have built some kind of ARMA model and you have, as using the method that we have already seen, you have forecasted certain values for 1, 2, 3, 4 and 5 steps ahead. So these are your forecasted values on out of sample. Because this is out of sample, you already have the sample values available, actual sample values to test. The approach to do is compute some kind of error measure. In this particular example, we'll use mean square error, mean absolute error and root mean square error. First step, we'll compute the difference between forecasted and actual values, which is the error. But generally there are two ways: either you take the square or the absolute value. Why we are doing this? Because if we are using some kind of summative measure, summation for positive negative values, they will cancel each other out. So large positive negative errors will cancel each other out and my measure will not be good. So generally a good measure is like mean square, mean absolute. They tend to take either square or absolute values of errors. So once you have the square of errors, you take the difference, which is your error. So your error will be and then you square it. You will get those values and then you can sum them up and take the mean. How to do that? So for example, these are our squared values. These are square errors. This is the squared number. Once we have the summation of this square, I can divide it by 5 to get what we call as mean square error, MSE. Squares and then divide to compute mean, and this is mean square error. Also, A more advanced version of this mean square error is root mean square error, which is nothing but the square root of this MSE. In this case 0.08, I can take the square root to get the 0.28. The second way is to take the absolute value. So again, I can compute the error f minus a, forecast minus actual, take its mod or absolute value, and then I can sum up all these values and divide by number of observations. For example, in this case, I have these absolute errors. I can sum them up all 5 and divide by 5 to get what we call as mean absolute error. To summarize, in this video, we have understood how to compare across different models by using some kind of error measures. These error measures like MSE, MAE, RMSE we have seen. There are more possible error measures, but please note they do not have any meaning in absolute sense. On their own, they do not have much meaning per se, when they are more useful in comparing across competing models. And why they are being used? Because we want to compare different models on their capacity of out of sample prediction. So using the actual and forecasted values from different models, we compute these error measures on the out of sample or hold out sample part of the data, and then compare across different competing models to compare their error values. On its own, these error values do not make much sense. We do not have a way to say that this is bad or good. Only when we have competing models and their respective errors, we can compare them across different error measures. Also, what kind of error measures are being used? That is up to researcher. In different cases, different measures are used. For example, when you are working with financial market returns, probably the positive errors are not so much as bad as negative errors. So an investor would rather like to have those models where, or evaluate a model based on its negative error, how much extremely negative returns or losses he is witnessing. Maybe he is not very worried about positive returns or gains. He probably is more interested on the negative side, negative tail of errors. So what error measures we are going to use, that is up to the researcher and the context, but these errors will be used on out of sample forecasting or prediction in comparing across different competing models. To summarize, an ARMA process is simply a combination of AR and MA processes. It can be easily identified on ACF and PACF plots as exponentially declining process on both the plots. To build an ARMA model, first we identify the order of the process. Next, we estimate the parameters through some kind of estimation procedure, such as OLS or MLE procedure. Lastly, we diagnose the model with the help of residual diagnostics and out-of-sample prediction accuracy of the model. For lag selection process, we use information criteria. One of the important objective here is to find extremely parsimonious model which fits the data well. In a strict theoretical sense, for an ideal model, the residuals extracted from the model should not have any discernible structure and should act as a white noise process. Forecasting with ARMA model requires conditional forecast for next 1 to S steps ahead. For those terms where information is available, the actual values are employed. Where the actual values are not available, conditional expectations are employed. Often, models appear to be extremely efficient when examined with the sample on which it was trained. This often leads to overfitting process, that is a very bulky and complex model which does not do very well in new data. That is why different competing models are tested on out of sample or hold out sample, which was not used while training the data. The two key terminologies in forecasting are first rolling sample forecast, which employs fixed window of sample, which is moving in a step-by-step manner. Second is recursive window forecast, where initial point is fixed and new data points are added and sample increases with each step in the forecasting process. The choice between the two methods is a trade-off between a sample which is larger in size versus that which is in sync with the current market conditions. Lastly, across different competing models, we compare their performance on out-of-sample forecasting accuracy through error measures such as MSE, which is mean square error, MAE, mean absolute error, or RMSE, for example, which is root mean square error, and then select the best model.